Welcome back. This is part C of concept video 11.2 is about series. Earlier we saw an example for geometric series, when is it convergent, when is it divergent, and then we also saw the telescoping series. Then we saw an example how to use the technique of partial sum and resolving into partial fractions method to find the sum of the series and determining whether it is convergent or divergent. This, in the earlier example, we should also, because the limit exists, we should also conclude that that series 1 over n times n plus 1 is convergent because we have a finite the limit is equal to 1, limit of the partial sum, and that becomes a sum of the series. That becomes a sum of the series. Because the sum exists as a finite number, the given series is a convergent series. In the next definition, we are going to define what a harmonic series is. Sigma n varying from 1 through infinity 1 over n, 1 plus 1 half plus 1 third plus 1 fourth. So if you plug in values n equal to 1, n equal to 2, n equal to 3 successively, you get 1 plus 1 half plus 1 third plus 1 fourth, etc., which is a divergent series. There is a beautiful proof for this. You can refer to that in your textbook. If the series sigma an is convergent, then the limit of the nth term equal to 0. If the series is convergent, then the limit of the nth term equal to 0. But the converse is not true. You can find out a series where the limit of the nth term is 0, but the series need not be a convergent one. So with every series, with any series sigma an, we associate two sequences, namely the sequence Sn of partial sums and the sequence an of terms. If sigma an is convergent, then the limit of the sequence Sn is S, and it is the sum of the series, like the previous example that we did, the telescoping series. The limit of the partial sum will determine the sum of the series. The limit of the sequence an would be 0 if the series is convergent by theorem 6. The converse of theorem 6 is not true in general. If the limit of the nth term equal to 0, we cannot conclude that the sequence the series sigma an is convergent. The reason, I can give this example. We just now saw what a harmonic series is, and we said that a harmonic series is divergent. But if you take the limit of the nth term, okay, so you notice that limit of the nth term for this harmonic series, its limit of the nth term, which is 1 over n, equal to 0. You notice that the limit of the nth term equal to 0, but the series it came from was sigma 1 over n, which is divergent clearly. So what it tells is that a series is convergent, but the limit of the then the limit of the nth term equal to 0. But the limit of the nth term equal to 0, the converse, is not true. If the limit of the nth term is 0, doesn't mean the series is convergent. Now test for divergence. If the limit of the nth term does not exist or the limit of the nth term not equal to 0, then the series is divergent. This is a very important test. It's the very simplest test of all. So whenever you start doing tests for the convergence or divergence, um, you want to eliminate the test for divergence, which is the easiest to test. So all you have to do is to take the limit of the nth term and see whether it is not equal to zero. If it is not equal to zero, then you can clearly conclude that the series is divergent. But if it is equal to zero, though, nothing can be said about the series. It is inconclusive. So you have to apply some other test. Show that the series sigma n square over 5n square plus 4 is divergent. So the very first test that we can test for is the test for divergence. We call it TFT from now on. So limit of the nth term is limit of n square over 5n square plus 4. Always, if you are given a series, then without the sigma, that will be usually, it is the nth term, as long the sigma runs from 1 through infinity. So in order to do this, we will always apply divided by the highest exponent of the denominator technique. So divide by n square, which will be limit as n approaching infinity, n square over n square, which is 1, divided by 5n square over n square plus 4 over n square. So this 4 over n square as n approaching infinity will become 0. So it is 1 over 5. So it is 1 over 5, which is clearly not equal to 0. So you notice here limit of the nth term is not 0. So you can conclude that the given series is divergent. So by test for divergence, the given series divergent. The test for divergence is uh, the very first easy one that you can look for to test the convergence of a given series. Next theorem. If sigma an and sigma bn are convergent series, then so are the series sigma c times an, the c is a constant, and sigma an plus bn and sigma an minus bn. And we have these following three properties. Sigma c times an is c times sigma an. C has got nothing to do with n, so that can come out of the sigma sign. Sigma an plus bn is sigma an plus sigma bn. It's kind of distributing the sigma. Then sigma an minus bn is sigma an minus sigma bn. Find the sum of the series sigma n varying from 1 through infinity 3 over n times n plus 1 over 2n. So let's take the first step. See, let's write down the given series. Sigma n varying from 1 through infinity 3 over n times n plus 1 plus 1 over 2 to the power n. So you're adding two terms. So we can, by properties of, by this property, by property 2, we can split them into two sums. That is sigma n varying from 1 through infinity 3 over n times n plus 1 plus sigma 1 over 2n n varying from 1 through infinity. So look at this. 3 can be taken out of the sigma sign because it's a constant. So we are using the first property here. 1 over n times n plus 1 plus sigma 1 over 2 times 1 over 2 to the power n minus 1. We want to write this as a geometric series type. So if you look at this part of the problem, the sigma 1 through infinity, 1 over n times n plus 1. We did this problem by recognizing this as a telescoping series. So we did this problem and found this using the principle of partial sum. And we said that the sum of the series was equal to 1. This was done in example 7. So I'm going to use that result. But if it was an independent question, you may want to prove it. Then this one I'm going to write like a geometric series way. It's A times R to the power n minus 1. That's the way you want to write in order to recognize this as a geometric series. So it is 3 times 1. This one I borrowed from the example that we did, example number 7. Plus, this is a geometric series, infinite geometric series with starting term 1 half and the common ratio 1 half also. So it is A divided by 1 minus R. A is 1 half. 1 minus common ratio is also 1 half. So it is 3 plus 1 half over 1 half, which is equal to 1. So it is 3 plus 1, which is equal to 4. So this is example 10. So we have a combination of telescoping series and a geometric series. And this was accomplished by distributing the sigma sign by using the property like this. So the rest of the problems, some problems from the additional suggested problems, like problem number 15, 23, 45, 47, 52, and 52 are done in my section videos. Please take a look at them. Refer to section videos on 11.2. Hope these videos help.